Evening, everyone.
Hello.
Good evening.
All right, are we doing okay with the week 5 probability questions?
I definitely do, but let me wait until anybody else asks.
Okay.
Okay, for 86C, just the results. What would be the result? I can tell you what I have.
Sure, go ahead.
Let me go back and see. 0.0215.
So 86C.
C.
Well, 86C, you're supposed to come up with the sample size is your final answer. So the first thing you have to do is
Or 86, yeah. See.
yeah. So for 86C, the first thing you have to do is figure out a Z-score,
Yes.
right? And then
Yeah.
you set that equal to the Z-score formula
Yeah.
with 20, over the square root of n, and then you solve for n backwards.
Yeah. So when I solve it, it's 0.0215 is what I got.
Yeah, you did something wrong in your math because you can't have a sample size of less than 1.
Okay.
Right? This
So basically 150 minus 160 over 20 divided by the square root of n, which is equal to negative 2.33.
yeah, that's perfect. That should be it. You
Okay,
just
150
just did something
minus,
wrong when you solved it.
okay. 150 minus,
I think it's probably this this double fraction, right? You have a fraction inside of a fraction, so it's probably that piece that tripped you up.
okay. I might have to try that, yeah. So
Yeah.
it should be like 0.1 or something, yeah?
Yeah, you should set this, like you said, you set this equal to your, your negative 2.326 is what I have. 3.3 is fine.
Yeah.
That should be close enough. But
Yeah.
when you do the algebra, you're going to get a sample size that's right around 20. It's a little bit bigger than 20.
Okay.
So do it again and make sure you get an
Okay.
answer that's a little over 20.
Okay, good.
Actually, that's the question that I was going to ask about too. So
Perfect. Killed 2 birds. All right, what else do we have?
Okay, let me copy. All right.
Dr. McBride, can you go over part 3 on the final project? What exactly kind of scenario you're looking for?
Okay, so yes, that's a great question. Everybody, has problems with part 3. They need to do a better job of the instructions for this one. Basically, here's how I interpret part 3 is, okay, so this week's homework, they had some questions. Let me pull up the question sheet and I'll just show you what I'm talking about. Okay, so in this week's homework, you had some questions that were random variables with a normal distribution, right? And you found some probabilities. So 4.65, 470 was using a normal distribution. Basically, a lot of these questions are pretty much the same thing over and over again, but these types of questions are really the exact same thing that you're doing in part 3. You're just doing it with a made up set of data. So let me show you the similarities, right? So down here in part 3, where is it? You're doing all this describing, and then these questions right here provide a detailed step-by-step explanation of the solutions to do these things. Are basically exactly what you did in this week's homework, right? Probability that the continuous random variable is greater than a specific value. Well, that's 465, question A and B. I mean, that's exactly what you did in that question. So for this one, right, for number 6, part I, all you're doing is describing the steps that you would take to solve that. Whether you did it by hand or in SAS or in Excel, doesn't matter, right? And then in your solution include the following. So you describe it and then you give a solution, right? So then the probability that a continuous random variable is less than specific. Okay, well, that's part C right here. The probability that a continuous random variable is between 2 variables. All right, well, between 2 variables is part D here, and then of course, part C here. And then percentiles of some data values. Well, a percentile is basically, you know, what you did right here with finding percentiles for 472B. And then graphs to visualize your solution. That is something that you guys will have to find online. There are numerous places online where you can get graphs of these things, but basically it's a graph of a normal curve that shows your solution. So for instance, the one that I use is StatCrunch, only because it's simple and easy and I have an account with StatCrunch. You have to pay for StatCrunch, but I get it free because I've been using it forever. So you guys can check out StatCrunch. They might like have a trial thing where you can do it free for a week or something. That's all you would need it for. There's also Vassar stats out there. But if you just Google search normal probability curve graphing tool or something along those lines, you'll find it. But basically, the nice thing about this is I go to the normal calculator and here is my graph, right? And let's just put this next to the homework question. So for instance, let's say we were doing 465 part A, which of course is also one of the questions that we're supposed to do in the final project. So our mean is 250, our standard deviation is 50, and we want to find the probability that X is greater than, well, 250 is silly, but we'll do it anyways, 250. The reason why it's silly is because we get exactly half. And this is what they mean by a graphical representation, a nice little pretty picture of the normal curve with it shaded in, showing you, and that's why the answer is 0.5, because it's exactly half of the graph, and blah, 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 okay? So that's the last part as far as graphs are concerned. Now, these first 5 parts where you're supposed to describe basically where this data came from, right? So the homework questions, sometimes they give you a scenario and sometimes they don't. Like for 470, they give you a scenario, they tell you where the data comes from. And that's kind of what you're doing in questions 1 through 5, only you're doing it for your dissertation. So the data for part 3 does not have to exist at all, because you can answer part 6 by just making things up, right? You can basically recreate these questions, come up with a different mean, a different standard deviation, you know, and some different numbers, and then compute the solutions. And like I said, whatever you're doing it for the homework, do it the same way here and just describe that, your steps, right? So did you use SAS? Did you use Excel? Did you use a graphing calculator? Did you use the formulas and do it by hand? Whatever you did, you're just basically providing step-by-step explanation of that. So this whole number 6 is basically just making sure that you understand this process. You're not just spitting out answers out of some technology. You kind of understand how the process works by putting in your own numbers and getting your own answers for a different scenario, right? So, okay, sure, you understood how you understood how it worked with these numbers. Let's make sure that you can create a whole different data set and still understand how it works. And it's a pretty basic concept, so I think you guys all kind of understand how it works, and you should be able to do that one fine. So that's the first thing that's confusing about this, is students think they have to have data. You don't. For 1 through 5, what I suggest is, if you are already far enough along in your degree that you've already started thinking about your dissertation, and you've already started thinking about the type of research question you want to look at for your dissertation, then please, by all means, use that for answering questions 1 through 5. If you have a research topic, and within that topic, you're going to investigate a certain question that is going to involve gathering data that would be from a normal distribution, i.e. you're going to be pulling data that's going to be a continuous random variable, right? As long as it's a continuous random variable, that's all it has to be. And then you have a normal distribution, because the central limit theorem tells us that no matter what the shape of the population is that we're sampling from, as long as we have a continuous random variable and our sample size is big enough, and by big enough, I think it only has to be about 20, well, anywhere from 20 to 40, depending on the different literature you read. I believe that anything over about 20 to 25 is big enough to guarantee the central limit theorem. Other people think it has to be closer to 30. Some people think it has to be closer to 40. There's no real definitive answer on it, but most of us in the statistics community agree that anything over 20 is a large enough sample size that the central limit theorem would apply. And what that means is that the one sample that you have comes from a certain population of data. That population can have any distribution shape. It could be completely uniform, it could be bimodal, it could be horribly skewed one direction or the other. It does not matter. The central limit theorem tells us that as long as our sample size is 20 or more, if we took every possible sample size of 20 from that population and calculated a mean from all of those different samples, and then put all of those numbers, into a set of data, that new set of numbers, i.e. the set of all of the sample means, would create a perfect normal distribution, and the mean of that normal distribution would equal the mean of our population exactly, and the standard deviation of that curve would equal the standard deviation of the population divided by the square root of 20. And then, of course, if we instead did it with a sample size of 25, then it would equal the standard deviation of our population divided by the square root of 25, i.e. 5, and so on and so forth. That's what the central limit theorem tells us. So if you're collecting data that it represents a continuous random variable, i.e. something that is measured. Remember, to be continuous, it has to be measured and not counted. So as long as you're collecting data, on a question or whatever it is that represents something that is being measured, then that sample will be one of a very large number of samples, because if you took every sample of size 20 from a population of even 1,000, that's going to be a crap ton of samples, right? It's going to be hundreds of thousands of samples. So your one sample is going to live on this normal curve that is created by the central limit theorem. Well, so if you are going to collect a continuous random variable for your dissertation, then by all means, answer these 5 questions in relationship to that research question. So let me give you an example. My research that I did my dissertation on was new teacher induction programs. And I looked at the different ways that we train new teachers and try to determine which characteristics of those training programs were most influential in keeping teachers in the profession, because there's a very large turnover of teachers. Within 5 years, 50% of all K through 12 teachers have left the profession. So we lose half of our workforce within 5 years of being hired. So one of the variables that I collected was a continuous random variable, and I could use this, thing. So let's say, so describe the setting in your problem scenario and a short background information. So the problem that I face is too many teachers are quitting the profession. 50% leave within 5 years, and it creates a financial burden. And so I want to look at what we can do to get teachers to stay in the profession longer. So then define exactly what you want to solve in this scenario and my solution plan. Well, i.e., I want to solve what causes them to leave and what we can do to keep them from leaving. And my solution plan is to, gather a bunch of data and look at it. So describe the type of data I'm going to collect. Well, I'm going to, get the age of the teachers, the gender of the teachers, what kind of degree the teachers got, what kind of subject they're teaching, what grade level they're teaching, how much they're being paid, and I'll stop there. There were a lot of other things I looked at, but that's the data I'm collecting because I think some of those might have a bearing on whether or not they stay in the profession or leave. Okay, describe the possible variables and are they continuous? Well, I just rambled off a bunch of them, right? Are they continuous? Well, their salary is continuous. Obviously, their gender is not, right? The subject they teach is not. The type of degree they have is not. What else did I get? Their age is continuous, their salary is continuous, number of years in the profession would be continuous, because it's still time, those types of things. Okay, and then describe the statistical methods that you use to analyze the data. Well, I would run, summary statistics on my numerical ones. On my qualitative ones, like gender and type of degree, I would just do a frequency histogram or maybe a frequency pie chart, to describe, to show the breakdown of gender, the breakdown of the discipline that they're teaching, the breakdown of, how many are in each, are teaching at each grade level and each subject, right? So what do we call it? Those cross tabulations. Remember we did those in the mini project, so cross tabulations would be good for those. And then for the continuous random variables, I would run regular summary statistics, the 5-number summary, maybe a box plot. I would run tests for normality to see if they come from a population that's normally distributed or not, to know, what kind of analysis I could do. And then I would run, a t-test or, this, that, and the other. These are more advanced things that you wouldn't have to worry about. But that's the type of thing, right? If you use software to get these analysis, cut the output and paste it. Again, I've got, far more stuff than you guys would need. You just need to pick one, right? So pick one simple research question, and then talk about one or more variables. You really just have to make sure that one of the variables is continuous so that you can pretend that you have the results for number 6 that come from that variable, right? So when you're making up these numbers, they're not just the numbers like in 465 where it's just 250 and 50. There's a scenario behind it, like in 470, where you have a mean and you have a standard deviation, but it's tied to some sort of scenario, and that scenario is based on your setting and all of this stuff. So it's our attempt to get you guys to start thinking in more detail about what you want to do with your dissertation. Because for a lot of students, up until the very end, it's just this arbitrary kind of thought in the back of their head that, well, I kind of want to look at this. Okay, well, you need to start narrowing it down. You need to start getting more specific. You need to start thinking about specifically what is your research question going to be? Specifically, what are you trying to solve, right? I mean, it has to pass the so what test. Somebody should read your dissertation and not say, so what, right? I mean, you need to come up with a problem that needs to be fixed. And then this is my idea of how we fix it. And if you come up with a problem that needs to be fixed and someone goes, you know what, it's already been fixed, or, you know, who cares, so what, we don't need to fix that, then you've got a problem. That's a bad dissertation. And there are a lot of bad dissertations out there. So the whole point of this is to get you thinking about that a little bit more deeply and come up with kind of some more concrete pieces of your dissertation. And if you're not far enough along to do that, well, then you can just make the whole thing up and go from there. But I'm hoping that all of you are far enough along that you can apply this to your dissertation topic, at least tangentially, if at worst. Does that make sense, Michelle?
It does. Thank you. All right.
Yeah.
And I hope you're recording this so I can go back and review it again.
Yes, I am. Yeah.
And do you need to see our hypothesis or question before we start to kind of work on this?
Well, that's what I was expecting us to do next week.
Okay.
So this whole part 4 presentation of your part 3 in a meet session, that's going to happen next Wednesday and Thursday. So I want all of you to have basically the idea of what you're going to use for questions 1 through 5 and present that. And by present, just mean, you know, this is my topic, you know, this is my setting. Basically just go through 1 through 5 very quickly. You don't have to get into a lot of details, but yeah, give me an idea of your research question, your hypotheses that you want to test, and we'll make sure that you're on the right track and it's something that's actually measurable and all that kind of stuff.
Dr. M, do we need to come up with a poster board or presentation?
No,
Okay.
great question. I don't want to, you don't need to, you know, you don't need to have a camera. I don't need to see you. You don't need to present, you don't need to share your screen. By presentation, don't think of it as that formal. It's literally, okay, who wants to go first? Talk about, you know, your topic and run us through just really quickly, you know, your hypotheses and how you would go about doing 1 through 5. And you don't even have to go through them one at a time. It's just, you can talk about it in one big thing. Okay, this is the research question I'm thinking about. This is the data I'd want to gather. These are analyses I'd want to run on it. You know, what do you think? And we can go, yeah, that sounds good. Or, you know, you might want to tweak it a little bit because that sounds more like a discrete random variable than a continuous random variable, or, you know, those kind of things. So nothing formal. It's just a real informal discussion of what you're thinking about, just to make sure that you've got the right kind of scenario.
What if, Dr. M, what if I already ran this by you and you said, okay?
Then you're fine.
Okay, cool.
Okay, thank you.
Yep.
I have a question on the final project, if anyone
Go for it, Cheryl.
Okay. So part 1, number 4.
Yes, this one's very tricky. Very, very tricky.
Yes.
So let me see. So the first thing you need to do, right, is you have to figure out the probability of a family purchasing more than 4 freights. And that simply just means you have to add up the probabilities for 5 and 6 freights. And if you look at the table of data for, you know, number of freights bought for a family, and you look at 5 has a probability of 2.5%, and 6 has a probability of 2.5%. So when you add those two together, there's a 5% chance, right, that they're going to buy more than 4 freights. So that's just step one.
Okay.
So step one is we know what the probability is. So we have a P of 0.05. So now we can run a simple binomial CDF with a sample size of 6, because in this one we had 6, right, families, and we're trying to find the probability that at least 5 of them purchased, right, more than these things. So our sample size is 6. Our number of successes is 4, because we're gonna do a CDF of 4, which is going to give us the probability of 0 through 4, and then we're going to subtract that from 1, and that's going to give us the leftover probability of 5 or more, right? 5 or 6. So sample size of 6, success of 4, probability of 0.05. Run a simple binomial CDF of that. Do 1 minus that, and that will give you the probability that a family bought 5 or more freights.
Okay.
Right? I'm sorry, that at least 5 of the 6 families bought 5 or more freights. So it's kind of like a double question. And once you calculate that probability, it will be very, very small.
Yes.
And when you calculate it and it becomes out very, very small, that tells you that it's very unlikely that this data came from
The same population of Germans on board the
exactly.
New World. Yeah, that's what I thought.
Yes.
I just didn't know. We didn't need to find the standard deviation of continuous, or I'm sorry, a probability distribution.
Not for
right?
4. No, not for 4.
Okay.
No, because 4, all you
Cool.
need is you know, the probability of 0.05 that you get from the 5 and 6 added together, the 0.025 and the 0.025. And then you just run a simple binomial CDF and subtract it from 1, and you're just figuring out a probability, a likelihood of this happening. It's basically saying, you know, what's the likelihood that these families came from this other population? Okay, well, if I give them the same probability of the other population of having 5 or more freights, then that's a probability of 5%. And then if I run a binomial, because it's either a yes or no that they, you know, bought the freights or didn't type of thing, and then I do that probability and I get a really small one, then that tells me that there's a very small chance that it came from this same population.
Okay. I
Now-
kind of got the last part, but I got confused on the actual probability because I used a normal
Yeah.
CDF as opposed to a binomial.
Yeah.
But I still got a small percentage though.
Yeah, because remember the normal is always going to model the binomial very closely, so the answers are going to be very similar.
Okay.
Now, I was looking at that first one, and like I mentioned to you in my email, that one, and I think that somebody else has a question ahead of me, but I had problems with that first one because it says to use histograms, but when I pull it up in SAS, for some reason there are no variables there to do those histograms. Is there something? What am I missing there? Because I load the data for that question.
You
But then when I
have
load it in
to
SAS,
you have to load the data, and then you have to use the probability as the weighting variable.
okay.
Because you know, for instance, like if you're looking at number of people in the family, and you've got the numbers 1 through 9 in your data set. Well, you would load the family variable in the analysis variable, but then down below there's a place where it says classify or weight or something. I can't remember what it is.
I'm not getting any variables to show up at all. That's why I was.
Oh, that's because you haven't cleaned your data.
Okay. Okay.
Yeah, so I put the data in the Google Drive with both versions because the original data has it has a bunch of crap at the top. So if you try and load it into SAS, SAS won't recognize the rest of it as data. So you have to clean it first. And I went ahead and cleaned it for you. But it's basically just a matter of getting rid of the top row of data, right? So you'll see that I've got part 1 data and the part 1 data clean. So if I open up part 1 data, here's the original data set. This row screws up SAS.
It also screws up Excel because I was having a hard time getting a histogram in Excel as well.
So what you want to do is just delete that one, and you'll see that my clean version of the data is basically the same thing, but I deleted that, and then I gave the variables names that make sense, right? So originally, all of these variables were just called probabilities. I renamed them so that when you load it into SAS, you don't have 3 variables that are all called probability. You're like, well, which one is which? You know that, this one is probability for families per parish, this is freights, and this is number and family, that kind of thing.
That was also confusing to me. And here I was nervous about asking because I'm like, what am I doing wrong? This is really not making sense. I look really stupid here.
Nope, it's a common thing. That's why I cleaned it up for everybody. And I did the same thing for part 2.
Okay.
Because part 2 also has the same problems with all this extra junk up here. You have to clean it up if you're going to load it into SAS. If you're going to do it in Excel, like calculating all these probabilities, you can do really easily with formulas in Excel, and you can just drag them and populate them as they are. So you don't need to clean them up so much. But yeah, with SAS you always need to clean it up.
Stick to SAS.
Yep. Okay, so somebody asked for 494B. So let me remind myself of what that one was, 494. Okay, so we didn't go over this one. The correlation coefficient and the p-value, they come in the display for the QQ plot. So if you remember, we did a QQ plot last in the mini project. Didn't we do a QQ plot in the mini project? Or was it last week's homework? I can never remember which. I think it was in the mini project. No, those are just scatter plots. All right, was it last week's homework? We did a QQ plot before. When did we do a QQ plot, guys?
I think on the first week or the second.
Was it the first week?
Yeah.
Maybe it was the second
yeah.
week. I think it was probably the second
like,
week because the first week was a lot of vocabulary.
Yeah.
The second
week, I mean, yeah.
Let's see. Yeah. No, maybe it was the first week. No, week 1 was all vocabulary. All right. Was it week 3? There it is. Yeah, but that one doesn't have. Well, when you run a QQ plot, we did it before in SAS. If you tell it to do the what is it? The inset variables, right? So let me just put a random data set in here. Let's have some good data. No, that's terrible data. That's all right. Who cares? All right, tasks and utilities. It is under. Isn't it? Is it distribution analysis?
Yes.
Yes, thank you. And then expenditures. And then options, right? We don't need the histogram, but we want the normal QQ plot, and then add the inset statistics. And then under inset statistics, you want the goodness of fit test. If you run that, and this one's going to look horrible because of my data, but up here is your correlation, right? So your normal test statistic is basically your correlation, and then this is your p-value. So that's the part that you need for that homework. Right, compute the correlation coefficient and the p-value. So there's your correlation coefficient and p-value. So if you just run a QQ plot and do that inset stuff and the test for normality, that's how you get part B for 494. And then for 488C, compute the exact probabilities and corresponding normal approximation with the continuity correction for 8 to 14. So with that one, let's see, we need probabilities, and I need to get this so I can see what the question is, so I can get the context for this one. So we've got n is 20, right? So there's our n. We've got a p-value of 0.5, and then they want the exact probabilities for 8 to 14. Well, if we do a binomial, so, and remember, what's very important is it wants strictly between 8 and 14. So that means you're really looking for just the probabilities 9, 10, 11, 12, and 13, right? So you want 9 through 13 because y has to be strictly greater than 8. So 9 is going to be the smallest and has to be strictly less than 14. So 13 is your largest. So you want the probabilities 9 through 13. So the first thing you do is set this one at 13 and run it. So there's 13. And then go back and set it for 8 and run it. What the hell? Oh, I ran the whole thing. And then take this number and subtract it from the 13, right? So if you take 13 minus 8, because remember, when you set it at 8, that gives you 0 through 8. When you set it at 13, that gives you 0 through 13. So you take 0 through 13, subtract 0 through 8 from it, and what you're left with is 9 through 13, which is what you want for that question.
Yeah, I got that one right.
All right, so is that good, Thiam? All right, I'll assume we're all good. Oh, yep, no problem. You're fine. Okay, so what else, guys?
This is Salpi. Dr. McBride, if you can go back to the final project.
Yes, of course.
1.
Yep.
So I just want to make sure I understand this, actually what we're supposed to do correctly. For part 1, we have, it seems like we have 3 sets of data in one file, right? And we're
Yes.
supposed to run all of those things for each of the data sets. So for example, the first one I did families per parish and families per parish probability. Great. That I didn't get can you get a histogram with that? It was more of a bar graph.
It's gonna look, yeah, it depends on what you do, but yeah, you can get a histogram from it. So let me get my data in here. So my data file. So final project 1, part 1. Run that. So that's an import 1. So you can see here's my data, number of families, and then probability, number of freights, probability, number and family probability. So this one is an old data file where I don't have the names changed, which is going to make it a bit of a pain in the butt, because now when I go to statistics and I want to run summary statistics, and I tell it to use import one, and my analysis variable, let's say, is going to be number of families per parish, this is going to be their probability. And that's where I have to come down here for additional roles, and your weighted variable is that one, probability. And now if I run this, there's my mean and my standard deviation for that probability distribution. Now, if I want to do a histogram, right, or a bar chart, histogram, my analysis variable, number of families, and then my scale, yeah, that's fine. And then my weight, I got to put in my weight. So it's going to be the one right underneath it, right? Again, you should use the one that they're, or you should rename them yourselves, but just make sure that you know you've got the right probability for the right group. And then if I run this, zoom out. There's my histogram. Now, obviously, that's a pretty crappy histogram. I'll want to play around with the bins and things like that, but that's how you get it going.
Got it. Thank you. Very, very helpful. I had it all wrong. Thank you.
Yep. The big thing for all of these analyses for part one is making sure that you're always weighting your variable. Because if you're just running it without the weight, then all it's doing is it's looking, each of those things comes out once, right? If I run it, it's all about, if you look at your where is it? See, they just have 1, 2, 3, 4, 5, and 6. I mean, they all should just be there once. And the only reason why these aren't that way is because they grouped. So if I went in here and did appearance and did bins and did 6 bins, there we go. 1, 2, 3, 4, 5, 6. It's thinking each of them showed up once, because in your data, it's just seeing each of those data values one time. You have to use the weight so that it has an actual weight to it. Now, I don't like the fact that this is showing 0, 0, 0. It could just be that it's not showing as many as I would like it to show. Or it could be that there's a problem with my original data set, that I didn't have it showing enough decimal places when I uploaded
It's in
it.
the
So
data set.
it
I
could
was
be
looking at that too, and it was in the data set. I thought it was part of the problem. Part of
yeah,
the,
it could be that I just didn't, so part one. Oh, it is 0. Okay.
Europe.
Oh, yeah, okay, because those do sum to 1. Okay, so they're supposed to be zeros. Okay, that's fine. I never noticed that before. But anyways, that's the whole thing about question number 1, is for everything you do, whether it's making a histogram or running summary statistics, you always have to use the probability as a weight variable, because it really is a weighted mean, right? Because each of your variables, right, each of your data values, right? So this is a variable, and then this is a data value, right? So number of families per parish, 1 showed up, 70% of the time, and 2 showed up 17% of the time, 3 showed up none, right? And so on and so forth. So you have to use this weight in order to get the proper, results, because it's basically, instead of having 70 ones and then 17 twos and then 6 fours, right? If you think about, these percentages and just rounding, you just have their percentages. And so that's what the weighting does, is it gives you the correct analyses. All right, anything else? Cheryl, do you have a question?
I don't think so.
Okay, I just saw that you were off mute, so I thought you had a question.
Oh, sorry about that.
No, you're fine. What about 486C? Okay, let's take a look at that one. 486C, how many blood pressures would be required so that the probability of failing to detect that the patient has high blood pressure? Okay, so this is one of those ones where you have to work backwards, to find a Z-score and then work backwards from that to find a sample size. So the first thing you have to do is set up this formula and then solve for this formula. So this would be the Z-score formula that you would use for 486C, because if the blood pressure exceeds 150, it's considered to have a high blood pressure, right? And blah, 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 blah. So if you read the whole context of this, it tells us that there's a mean of 160 and a standard deviation of 20. So there's our mean of 160 and our standard deviation of 20. And then the Z-score formula is X minus mean all over the standard deviation divided by the square root of the sample size. So this whole thing about the probability of failing to detect, well, if you read through these questions, failing to detect high blood pressure would be a reading that's below 150, right? Because it says if the blood pressure exceeds 150, they're considered to have high blood pressure. So if their readings are below 150, then it would come back and you basically think, okay, they're fine, their blood pressure's fine. So that's why we're looking for a Z-score of below 150. So basically what this is representing pictorially, right? And I always like to draw a picture of a normal curve so I know what the heck is going on. Is I've got, let me make this bigger so I can play around with this. We've got our normal curve. And the mean, right, is always in the middle, which is 160. And the idea is if we get a reading below 150, this is all considered, normal blood pressure, i.e. we would fail to detect that they had high blood pressure. So it's the idea that if they did have high blood pressure, what's the chances of getting a reading down here? Well, we know that on a normal curve, they said the question that we're answering this time is how many, like how big would the sample size have to be so that the chances of this happening is 1%. Well, as the sample size goes up, what happens is you're dividing by a larger and larger number here, right? So your overall standard deviation is getting smaller and smaller. So as your sample size gets larger and larger and larger, what happens is your normal curve just gets thinner and thinner and thinner. And so now, here's still your mean at 160, but 150, right, is way down here. And you have very little, right? The idea is how big does our sample size have to get so that everything scrunches together so that the chances of being down here is only 1%. And if you go to SAS and go to our probabilities, go to our code, right, and do the normal stuff, down here, our normal quantile here. This says normal values from probabilities inverse for less than our given probability. So we want this to be 0.01. We have our mean is 0 and our standard deviation is 1. This will give us a z-score because a z-score is always on the standard normal curve, and the standard normal curve has a mean of 0 and a standard deviation of 1. If we run this, you get the negative 2 point, I know it's hard to see. You get that z-score. So what that tells us is that we're looking for a z-score of negative 2.32635. So what, because that'll be 1%, right? So on any normal curve, if you're negative or basically 2.3 standard deviations below the curve, so that's why it's negative, right? So almost 2.5 standard deviations below, there's only 1% of the data left behind. And remember, the empirical rule tells us 68, why is it not? There we go, 68, 95, 99.7. So this is 1 standard deviation, right, in both directions, 2 standard deviations in both directions, 3 standard deviations in both directions, captures that much data. So you can see that if we go out 2 standard deviations, we got 95, which means there's 2.5 below and 2.5 above. So we know that it has to be a little bit more than 2, but definitely less than 3, because if we go 3 in both directions, we only have 0.3% or, 0.15 in each tail, and we want 1%, not 0.1%, right? So that's why it's 2.36. So we basically go down, 2.3 standard deviations away, and that gives us 1% in the curve. So if we set this equal to negative 2.326 and solve for n algebraically, that's where you're going to come up with your sample size. You're going to get n equals something, and it should be right around 20-ish. All right, a couple minutes left. What else we got?
After all that, I got a headache. I haven't been challenged like this since undergrad Greek. 7 o'clock in the morning with a teacher that looked and sounded like Mr. Mc.
Stats can be tricky.
I still love it.
When I was in graduate school, we one of the things we had to do was basically prove Pythagoras' theorem, prove a squared plus b squared equals c squared, and it was a 50-minute class, and we had chalkboards on all 4 walls of the room. There were no windows, and the professor started on the front chalkboard and just started going all the way around the room because he was running out of room, and he went around the room twice, changing variables probably 6 times, and we were just frantically scribbling down everything he said for 50 minutes without a break. And at the end, one of my friends looked at me and goes, "God, I feel like I just gave birth to an accountant." And that's what it feels like when you don't understand. I will never forget that feeling, because I'm sure that's what you guys feel like sometimes when I explain this stuff, is you just feel like it's just a wave crashing right past you. So digest it and then come back and listen to it a little bit later, and it'll make sense. But yeah, it's stats is fun once you get to know the basics. All right, anything else before we go?
Thank you very much. I will send you my final draft.
You got it.
This evening. Yeah, thank you.
Yep.
Okay. So.
Anybody else?
So next week is our last class,
Yes.
and it's not mandatory if we submit our final project before then.
Correct. Well, it's not so much you have to submit your final project. As long as I've signed off on, yes, we do have a meeting tomorrow night, same time as, well, not same time as tonight, but same time it's been every week, which is a half an hour earlier. Yeah, as long as I've signed off on your dissertation idea, you know, your research question that you're going to use for the project, you don't need to show up and discuss it.
Okay, very good. Thanks, Dr. M.
You're welcome. And I expect next week it'll be rather quick. I think next week's meetings will be quicker than normal because it'll just be, you know, the 7 or 8 people who show up that present their topic real quick, and we'll discuss it and see if there's any problems or holes, and then if anybody has any questions about the final project, we can discuss it and then get out of there. All right. Well, great job, everybody. Be sure and post questions to the doctoral you know, dialogues so we can you know, talk about them as a group. And if I don't see you tomorrow, then maybe I'll see you next week. Thanks, everybody.
Thank you.
Yep.